Welcome, Tim. He is from Red Naga, and he's now going to give us some details in the analysis sector, specifically for Android compiler fingerprinting.
Cool. So again, my name is Tim, and thank you guys for having me. I promise that this talk is more interesting than the title sounds. So sadly, my co-presenter was unable to make it. Turkish Airlines is horrible, and don't ever fly it. So who are we? Who's Red Naga? So essentially, Caleb and I used to work together at multiple places. We have a friend up in Washington State who's great at just breaking all OEM devices. And essentially, we were just like, you know what? We all love hot sauce. We like alcohol. We like finding O-days and embarrassing people within good fun. We like fuzzing, and we like just to, break bad people's infrastructure and make their lives hell. So if you want to join us, the only requirement is that you take a video of eating a really spicy pepper, whatever your level of spicy is, that's cool. And then you just make a blog post. So it's all open invitation, and you just have to do good, whatever that means to you. The main purpose, I would say, that we really formed this, though, was we wanted to up-level the community. And I think that, everyone in this room is most likely incredibly smart and very good at something, whether it be sysadmin or fuzzing or developing security architecture. But this is honestly me standing on a soapbox and saying, we can all help each other. So doing that through open source or just chatting with each other, whether you work at this AV company or that AV company, sharing samples. This is how we get better. This is how we make bad people have to spend more money. So if you would like to join or just help people out, just keep doing that. That makes everything harder for bad people, and that makes our lives easier. And that's basically the initiative behind this talk, is us trying to open source things and make it so that you guys don't have to recreate the wheel, because what we're going to demo is essentially something that every AV company tries to do. Some succeed, some do not. But everyone always hides behind the fact of, like, this is secret sauce, we're going to patent this. Everyone does it. So why not just open source it and let everyone start at the same level and just start working from there, opposed to just recreating everything. We also have lots of training for how do you find O-days on phones online. So please check that out. We put a lot of work into it. And all these trainings are free. If you would like to license them, then you can pay us, and we will donate that money to charity. That's where a lot of our bug bounties go. So again, join us and eat some spicy things. Specifically, Caleb, again, is the one who is not here. He is a security researcher. He worked at SentinelOne and at Lookout with me. He's a brilliant person who basically hates doing the same thing twice. So he's going to basically automate the crap out of everything. And you should go check out Simplify if you've ever had to deal with obfuscation. It's basically, we were looking at DexGuard and Dex Protector and all these things, and it was basically, his motivation was, this sucked, I want to make this fast. No one else should ever have to do this painful thing ever again. And so it's basically an emulator for Smalley, which is going to go through and simplify all the instructions so that if there's random math operators or XORs, it just blasts those out. So that's all open source. That's on his page. And I added a picture of him with his dog because he says that this makes people think you're more trustworthy. So I also have a dog, and I'm more trustworthy now, too. Like Caleb, I worked at Lookout and SentinelOne. I currently work at Cloudflare. If you want to talk about Cloudflare bugs, you have to buy me a beer. If you would like to talk about anything else Android-related, I will buy you a beer. I really enjoy fuzzing, obfuscation, and breaking Packers. So if you make any of those, please taunt me so I can break them and talk about how crappy it was and all that kind of stuff. Why we were here and why we are here. Threat intel is really important, especially when we're trying to think of where should we research next. Where are people currently attacking us? Where might they start attacking us? A lot of people complain about some of the things that we have talked about in the past, saying, oh, if you tell bad people how to evade us, then they're going to evade us. And we say, great. If we tell them how to evade you, then you should be anticipating the evasion. Therefore, you can funnel all their money and their effort into trying to evade you, and you already know where they're going to go. So if you can funnel bad people into these certain directions, I think it's a really strong point on how you make bad people go the way you want. So give them hints, maybe not all the hints, and then start just anticipating their next move. We also just thought that, by releasing this, hopefully, again, you guys don't have to reinvent the wheel. Hopefully you understand the tactics we're taking, and you're able to just build on top of that, hopefully give us some pull requests. We also heard Austria has some really good beer, and that's maybe the real reason we came. So the takeaways today. How can you fingerprint Android compilers? What are abnormalities in AXML and in the DEX structure? We've given multiple talks in the past that dive really deep into this. We've discussed how you create packers and how you can try and evade different analysis tools. And basically, this was the culmination of all of that. And how can we detect these things, and how can we go really fast? Why we wanted to do this was basically we had some hypotheses, and we wanted to prove them out. And nobody really wanted to fund this research, so we said, screw it, we're going to do it ourselves. Related things are Flirt, if you've ever used IDA, and then PEID. We basically stole their name, and those people are great and basically go down in history, and maybe one day we'll be known for something other than making fun of people. So current Android tool landscape. This is going to be a brief overview, so hopefully this maybe teaches you guys something, and if not, it'll just be a quick refresher, so try not to glaze over on this. This is an APK file. You have your meta-INF. This is for the old signing stuff. But basically, the only part we really care about for an APK file, which is a zip file, is the Android manifest, things in the XML directory, and the classes.dex. And these are the only kind of resources that we really care in this presentation. So essentially, an Android manifest, this is going to contain all your entry points. So as a reverse engineer or someone who's going to be automating things, essentially, this is going to say, where are the entry points into the code? What kind of services might be running? What kind of permissions does this application say that it wants to use? So you might be analyzing something, and if it says it sends SMS, you might expect it to. If it sends an SMS and it didn't say it was going to, there's something weird going on there. We're able to reverse these type of things with a couple different tools that are out there. We've created some O&O editor templates that are pretty helpful for forensics uses. And there's a bunch of just open source, and there's some paid tools in there. Normally, and this is specific to this talk, you're going to see that normal developers use AAPT. This is going to be used just under the hood when you're using Android Studio or whatever your build chain is. Most people don't even know what that means. But essentially, you're going to create an XML, and it just gets compiled. What's interesting is there are essentially three tools-ish categories. Most people use AXML printer, whether they know it or not. There's a couple modified versions of that, an APK tool. And so essentially, this is how you could create or potentially modify one of these files. But it's interesting to know that a normal developer should probably never do this. There might be interesting reasons to do this, but most will not. So one of the things that we had for a hypothesis was, okay, so if you're modifying things post-compilation, you potentially don't have the source code, or maybe you're injecting something bad, or maybe you're a packer and you're not actually sending down a tool chain for the developers to use. So you're doing something post-compilation. That should be interesting for most analysis. Most people who are looking at applications want to know whether this was truly from a developer, and then you can decide if that developer was good or bad, or if it was from potentially a trusted developer, and then something has happened to it. This project led me down kind of a rabbit hole where I started refactoring some code to open source. And it was really interesting to me to just see the lineage of this code base. We saw a lot of people targeting this to try and break it, mainly out of China. People were releasing binaries to break this. And what ended up happening was APK tool apparently took a bunch of this code, and then they rebranded it and stripped off the licenses. So you might not know that it was actually that code base under there. And then it turned out Jeb was using APK tool under the hood, and these, so Jeb is a professional tool that people pay a couple $1,000s for, or something like that. And essentially, high-profile reversers might be using it against high-profile binaries. And these things were breaking the tool. So magically, you saw that this guy backported a fix into the open source tool. And so it was interesting that you could see that all these tools were based on the same open source library. So basically, with one breakage in one library, people were able to defeat most of the tools that were currently out there. We rewrote this. It's actually going to be refactored, and there'll be new code pushed up because we discovered some new nuances in AXML stuff. But essentially, this avoids all previous breakages. It can be used to detect changes and also inject things and just basically modify this stuff. So this is just, I guess, a little shout out to our own little project. Feel free to use this. It's picked up some steam over the past year, so that's good, and it's actively maintained by us. So the next part is, again, the classes.dex. This is essentially all the class files are going to be compacted down into a dex file. I don't really want to go too deep into this. There's a whole presentation we did many years ago at Black Hat. There's lots of tools to reverse this. The bulk of them revolve around Smalley or APK tool or consuming the output from that. Again, you do have, these are all the open source ones. This might be really interesting to the students who potentially want jobs in the future. Smalley was open source, and then Google said, hey, you should come work for us. Injarify is open sourced and was started by someone at Google. The creator of AndroGuard then went to work at VirusTotal, which then got consumed by Google as well. Dex2Jar was someone out of China who got consumed by Trend Micro. So a lot of these projects, oh, and Radare was consumed by NowSecure. So if you do a really cool open source project, someone probably wants to pay you for it if they start using it. So that's a really great reason to do some open source work. You also have for pay applications and Jeb, pardon, this is the wrong slide, but essentially we see the cross collaboration of a lot of these tools being used in other projects. So usually when we're trying to break things, we shoot for the lowest common denominator, and we're able to usually break multiple tools with that. For disassemblers, so that we can start looking at the actual code, that's essentially going to be these tools, opposed to the following tools, which contain decompilers. So you're going to have different types of reversers and different types of tools built on these. A lot of people in the Android space tend to try and decompile Davit code into Java code and then use Java source code analyzers on those. Different approaches for different things. It really just depends on what you're looking for. A lot of these are scriptable. That can be good, useful, especially if you're going to try and analyze hundreds of thousands of applications. Just basically for forensics purposes, and a lot of what we pulled in for this presentation was based off of O10 editor templates that we had heavily modified to look for nuances in the files. So how are these DEX files created? And this is honestly, it's super nerdy, but this is where we really got interested into it. Basically, there are 3 different types of compilers that are normally going to be used. DX is the normal thing that most developers are currently using, and it's just what's shipped with the Android SDK. They recently released, I think this is for Android N and above right now, is Jack, which is a different compiler, and the outputs of the same code with these compilers do look different. And Dex Merge is a really interesting tool that apparently no one has really ever known or used, because a lot of people just use Smalley to inject, decompile a file and then inject Smalley and then re-Smalley the file. Apparently a lot of people didn't notice that you could just pipe 2 Dex files in Dex Merge and it just mashes them together and all that stuff will just magically work. It's a really cool tool, but it produces a different class file than might normally be seen, and we'll go into depth about that. So the next 2 tools, basically they all use DexLib. Smalley has DexLib 1, 2, and 2 beta. They're constantly working on new ones, and these ones are the really interesting engines to us because essentially if we took a normal class file from source code and then we decompile it and then recompile it, it's going to have a different hash. So clearly something's changed, but what has changed? And that's what we're going to dig into. And these are really interesting to us because that means someone has modified it from the source. So compiler fingerprinting. Caleb just threw together this analogy. I think it's really interesting. And essentially, this is like a super low-tech way to describe what we were trying to do. So essentially, you can hang clothes many different ways. And apparently, Caleb is left-handed, and his wife is right-handed, which results in 2 different styles of hanging up T-shirts. They're both valid, and they both result in a T-shirt being hung up. But what happens is you basically have and he actually put some algorithms down. But they sort their they sort his T-shirts in different ways, but they're both still valid. And you can both find actual shirts. So it's an easy way to produce a valid closed compilation. And essentially, these are two different compilers that are looking at it. But what is interesting is he literally does this, and this is why Caleb's insane and I love him. They can figure out who put things away and if it was hidden based on who hung it up and how. So he's able to basically say, like, I don't even know the last time I did laundry, but I definitely hung it up because I hung it up that way. Or, where's that T-shirt? And it was my wife who hung it up because it was hung up a different way, and that's why I couldn't find it. And apparently, yeah, maybe that person wants a divorce now. But so that's essentially what we're trying to do, is figure out who did this. Because all I have is a big library full of shirts, and I want to know who put them away. So first off, with AXML files, they're relatively simplistic. Most tools, when they're injecting things, are appending new structures to the file. So they're not going to take the current structure and inject into the middle, because nobody's really cared to ever do that. So it's really easy to just basically decompile your XML file, and then people just throw things on the bottom. Android will respect that, so even if you have permissions at the top and a couple at the bottom, doesn't matter. So this is what the normal file is going to look like. This is normally what AAPT is going to actually output. But what you'll see for pirated things or when people inject malware into it is all of a sudden you got a couple permissions at the bottom, and then all of a sudden the orders aren't really in the same order anymore, like they're not sorted properly. So it's a dead giveaway that someone has done something. We have seen, since the time we actually started doing some of this work, some people were injecting permissions in the right spot. So it's interesting to us. And what we can do from here is basically say, not only did someone inject into here, because we can see it in different ways, we see that they're advanced enough to care about putting permissions in the correct order. So for normal AXML files, the bulk of the applications are going to put things in this, it's basically wide character format. And this is just a snippet from O&O editor, but essentially what we see is this is version code, and this is just a normal string, but it has null bytes in between. So this is all based on a flag that's actually in one of the resource headers. Sometimes what we see, and this was actually a breakage in AXML printer, was because the person didn't read the spec. And the spec basically said it's possible to end up putting this flag in, and then all of a sudden you're not going to have any null bytes in between. And so the AXML printer original author said, oh, I've never seen this, I don't understand what this does, so they didn't put it in there. And so the first time we had ever seen this was someone actually just trying to break those tools. So all of a sudden, none of these tools worked, and that's when the Jeb author started backporting things in. So it was in the spec, this was valid, this was respected by all the Android devices, but all the analysis tools started breaking suddenly. So what we ended up doing with APK ID, to just flash forward, was you're able to write simple Yara rules, and Yara is just a really simple Swiss Army knife kind of regex searcher. And based on the modules that we've created, you can basically define parts of the application. So this is just supposed to be a really simple example of, I wanted to say, how many of these Android XML files do not have a flag of 0, or do not have a flag of 256, which would be a UTF-8 flag. And then which ones do have a flag of 256. And so I just quickly ran this over about 85,000 APKs, and only 20 had a UTF-8 flag, and only 3 have a sorted flag. And I didn't dig into exactly what are these files doing and why are they doing that, but immediately this is an interesting way to take 85,000 files and go, who's doing something a little different than everyone else? So now you have 3 files to look into that are potentially doing something weird. And then you have 20 that are specifically doing something a little strange that used to break a lot of analysis tools. We also see that there were more protectors and anti-tricks. This one was kind of interesting. This is the output from the unfixed version. Basically, it just blows up immediately after it starts that first line of the AXML equals whatever. That's printed out for absolutely every file because it's a given that this is going to be an XML file. And after reading the first part of the header, it just dies. It was expecting a value. But these values aren't actually expected on Android devices, or not all Android devices. So basically, by not putting specific tags in, they started breaking analysis tools because, again, the analysis tools actually did read the spec, but the Android devices were basically like, well, I know it's always going to be there, so why do I bother reading it? So it was interesting. DexGuard started implementing this, and then we saw some bad people who weren't even using DexGuard immediately pick up on this technique to start actually breaking different analysis tools. APK tools specifically was pretty easy to fingerprint. Some versions just go, hey, guess what? I built this. So that's kind of a dead giveaway that they built it. Cool. So onto Dex files. This is where the more interesting and more in-depth and weird, nerdy things are that we ended up finding. Dex files are really, really flexible. And if you read the spec, you can just mangle everything in the binary, and you can have them pointing to different ways, as long as it's inside the binary. You can't point outside of it. That was fixed a long time ago. But you can do really interesting things and rebuild them on the fly in memory, all that kind of good stuff. So what we did is we basically took all the known tools out there, and we took a known input, and then we rebuilt them. And then we started comparing them all in O&O editor from like a forensics level. All the hashes don't match, so we ended up just saying, okay, what is different? I mean, the source code is the same. Did something get optimized out, or like what's going on here? We read a lot of the source code. We read the spec. None of those match up in the fashion that is Android source code. And this is how we find differentials and parsers. So this is a really interesting way to find different characteristics, if not a very long and painful process. So some of the things that we ended up finding that are really interesting. Class interfaces, class paths, the endian tag, header size, link section, string sorting, map type order, and section contiguity. None of that means anything to you guys probably, but I will show you what they mean. So essentially, abnormal class interfaces between Dex and between DX and DexLib. This was really simple to find, but honestly, like these are both valid use cases of interface offsets. So the normal compiler will just say the interface offset is 0, which makes sense. And then DexLib would say, but it's null, and null specifically located over here. These are both valid, but this was a dead giveaway that DexLib was used or a normal compiler was used. For abnormal class paths, this is actually, I believe, protected by DexGuard. And these are interesting things because normally what Smalley does is it's basically taking all the original class files and trying to recreate them on a file system. And we've seen this attack for a very long time, but specifically DexGuard was using invalid Windows names for a lot of these paths. So con, prn, aux, clock, these are all things that are not allowed to exist on the file system. So as it was trying to output it, it was breaking these things. We showed this many years ago, and people just keep picking it up. This one was a anti-decompiler technique as well. Basically, this is an old jar attack. People used to do this on Blackberries. Basically, a zip file just contains the file length or the file path as a string. And in a zip file, the format says it can be almost infinitely long. It's probably like a 32-bit integer. But on a file system, it's usually 255 characters. So if you then try and have a string that is 300 characters, try and dump it to a file system, that's a no-go. Really easy hack, really easy to evade, really easy to fix once you've seen it a few times. Abnormal Indian magic. So every Android file is going to be Little Indian. It is theoretically possible to make a big Indian one, and the Dalvik optimizer will try and re-optimize your binary and switch all the bytes around. We created a big Indianer, and if that's even a word, I don't really even know. But it doesn't actually work on the device, but there's tons of code to actually try and switch everything around. So in theory, it should have worked. Maybe we had a bug, but honestly, this was painful, and it'd be interesting to see in the wild. We've never seen this used. Header size. This is an attack that we showed, again, probably like 5 years ago at this time, where we did we injected a Dex file into a Dex file by just expanding the header and saying that the header is going to be like 1 meg large. Inject your file in there, and then once you boot up, once it's actually running, you go into your own memory, and then you look for the file you've injected into your memory, and then you would unpack it and just start expanding. And this actually broke a lot of decompilers because they were saying, you know, the header should only be this size. I don't support anything under that. or over that. So basically, we were able to inject files in there. Abnormal link section, this was found independently by like 10 different people. John Sawyer found this, Caleb found this, and then I found malware authors using this, and then I talked about it at Black Hat before I had actually met those two guys. But this one was cool. There's just basically something called a link section that DEX files have never used, but you could change it, and you could turn it on. And things were anticipating that this is always 0 because nobody knew how to support it. So this was an interesting thing that you can sometimes see still in the wild, where people are setting these flags, and they're telling it to point to certain ways, and Android will still just respect this and let the file exist. This is where it starts getting super nerdy and interesting, I think. This is a specific to DexLib1. Essentially, so the string index order must always be in alphabetical order. So these are the offsets that point to the strings. But these strings do not have to actually be in order in the data section. So some compilers put them in order, and some of the DexLib ones do not put them in order. In theory, you could have the strings absolutely anywhere, as long as those offsets are in order for like alphanumeric. So this was a really interesting and wonky way to actually fingerprint between DX, Jack, Dex merge, and DexLib. Abnormal type order. So there's a map section at the bottom of a Dex file, and essentially it says all those sections that you want to know about. If you go down here, it'll be like, okay, it's up here, it's up there, it's up there, it's up here. These are always in the same order unless you've used a different tool. So DX always puts them in this order. Dex merge always puts them in a different order. So this is another fingerprint that we can use to say, like, someone has used this or someone has used that. And then this one was something that we couldn't necessarily pin down. It often flags Dex merge, but it sometimes has happened in cases where we can prove it was not Dex merge, but we could not prove what it was. So this might be like a weird edge case in one of the compilers, but it basically was like, whoa, look at this binary, because something's really weird. Basically, the way those sections are lined up, there's usually not much empty space between them. But in the case of Dex merge, it starts giving you extra space between them as potentially a buffer, because maybe it's anticipating more data and then it doesn't use it. But essentially, the type offset section is usually butted up right against to where all the data is. And then sometimes it isn't. So this was an interesting flag just to throw in there as a feature. So why did we do all that? We did it because we were thinking, I wonder if we could use this for malware or piracy detection, or to just find interesting things in the wild that we just hadn't seen before. So again, there's 4 main, we'll call them compilers. There's DX, Jack, Dex merge. Those are legitimate things that people would use. Again, Dex merge is something that's not often used, so this makes it more interesting to us. And then we have Smalley, which is DexLib, and there's different versions of that. So this was specifically interesting to us because we would just assume that they might not be legitimate, because if you were a legitimate developer, why are you compiling your source code and then modifying it? Why aren't you just modifying your source code and then compiling it? So again, DexLib probably tampered. This probably relates to pirated or cracked apps and potentially malicious apps. So what we did is we took a sample set. We did about 20,000 from each market. Markets were Google Play, Aptoid, Black Market, and there was another one in there. And then we took 10,000 of the highest scoring fraudulent apps, and this is when we worked at Lookout, and we had a machine learning based thing that basically said these are bad, these are good. So you would assume that things that we're saying are bad should be bad. So we want to look and just see, like, inside that subsection, do these look fraudulent to us based on these fingerprints? And then we grabbed a bunch of actual malware samples that we know are bad. And we wanted to see, like, so are people compiling all these from source? Or are they modifying them? Or, like, what's going on with malware? Does malware look completely different than normal binaries? So the method was scan the DEX file of each of the APKs. We didn't specifically look at the AXML. It's hard to say exactly why. Using Yara and a Yara module for AXML is kind of wonky. Still working out some kinks in that. And so by looking for weird files or flagging files as weird, it meant that there was an abnormal string sort, a class path, or a type order that had changed. Weird means it would be these things that we couldn't exactly pinpoint, and it was header size change, type descriptor, class path, or abnormal Indian magic. And this is what we end up seeing. So the top one is all malware, meaning that there was a good percentage of malware that just looked normal. And then we saw lots that looked tampered. In the fraudulent bucket, we saw a little bit less that are tampered. In black market, which is basically all pirated applications, so you would assume that a lot of those have been tampered to be cracked with, that would end up being about 20%. Aptoid, there seem to be a lot of things that were modified. Aptoid is basically a backup of people's devices. So you basically install this market, and it basically uploads all your applications. So these are things that are just residing on people's phones. And essentially, there was 15% of them looked tampered. In the Android market, top apps, when we pulled 10,000 apps from like the very top, like the ones that people are downloading, 4% of them were tampered, and a sliver of them were weird. And then the other ones are just from another market, similar to Google, and 12% of them seem to be tampered, and there was about 0% that were weird. So what does that actually mean? I mean, this was interesting to us just because, so the malware samples apparently don't all seem to be compiled from source code. The top Android market apps, this one was really interesting to us because we were like, are these malware? And then you look into them and it was, oh no, these are people that are downloading security tools and they're running them after they've compiled their binary. So there's packers, there's strange obfuscators, that kind of stuff. So I don't remember if we actually found any malware in the Google Play out of this subset, but it's just interesting to see that someone who's maybe in the top 1,000 or so in Google Play is going to the extent to modify their application post-compilation. And then specifically for the malware tampering, we thought this was pretty interesting. It was 756 malware families with lots of variants. And we took a subset of those, and about 50% of the families end up having some tampering, and then 50% of families had no tampering. And then there were some families that were just 100% tampered, which is kind of weird. So if you're a malware author, you would think you'd have the source code, but apparently they never had the source code, and they only released binaries that they ever injected things into. So it's just kind of interesting to try and profile an actor as you can maybe see that, okay, they had the source code and then they lost it. Or maybe they sold the source code and then someone else started just injecting into their malware. So these are families that we had named at Lookout, and I don't expect any of you to actually be able to read into those. Some of the interesting ones are, so there was Sandro Rat, which was basically someone had taken Andro Rat, which is an open source rat, and they only inject into it, even though they have the source code. So it was just interesting that they basically compiled the binary and then they wrote something around it to decompile it, inject some stuff into it, and then recompile it, opposed to just compiling the source. This is an example of a Russian family that we had been tracking for probably 3 years. It was the biggest pain in the ass. It changed every week. We basically were able to map them to release cycles. So every Tuesday, they would stop shipping one binary, and then about 4 hours later, they would start pushing another binary. What was really interesting to this, just as an organization of security analysts, was why are some of these families tampered, and why are some of them not tampered? So the red means normal on this, basically meaning that they compiled this from source code. But we see like alpha SMS N, someone tampered it. Is that the author like shipping a binary and then injecting something into it at the same time? Is that another group taking their binary and injecting into it? It's just strange. And then it looks like they started tampering with some anti-decompiler tricks in there as well. And so this was actually a really interesting signal to us because we basically went, did we screw up? Maybe we classified this wrong. We should go back and revisit these things. And so as you can see, this is a subset of the variants we had. So there's so many variants here. So we're able to like drill down and then go, oh wait, this was a different campaign. This looks like the same one, but it was something different. We should look deeper into this. And then that spirals out into a different family. So as a conclusion, tampering is a good signal for someone doing something bad because they're tampering it. Shocker. And it was also just very interesting to see like how you could use this to profile actual bad actors out there and what they were doing and what was going on with their code base. So right now, I want to show you a demo of essentially what APK ID is. Let's see. So I just have a bunch of hashes in here. These are all APK files. These ones specifically were weird because I was doing some tests with them. And essentially what you would do is APK ID, it's just a command line utility. You can have it pipe out JSON, and basically you could use this as like a little tiny microservice. You just stand something up that consumes a binary and pipes this to it, and then you can consume the JSON at the end. Or you can just have it recurse across a directory. And what we start seeing is we have rules in there for anti-VM. We have rules in there for, let me stop this. So, here, make that a little more visible. So what we see is, this file seemed to be used by Dex, or excuse me, seemed to be compiled by DX, but it also has flags that said this might be Dex merge. So that might be interesting. We have DX, and then this one right here specifically has anti-VM checks, and we know it was compiled with dexlib 2. In here, we've also added packer rules, so we can clearly identify that this is Tencent. This means that maybe you want to put this in a pipeline of automation where you say, anything that's packed with these known packers, we have known solutions for that. Pipe it into the Tencent on packer. And essentially, we just wanted this to be very much like PEID. What kind of protections are in here? What kind of interesting features are in here? And what was the compiler? So from this, we suggested that someone do some machine learning on it because, it's the security world and it's a buzzword, and if you throw it in the cloud, then you could probably get some VC funding around that. So essentially, Caleb went, okay, nobody did it, I'll do it. And this is a tool that he plans to open source. Currently, he just stood it up at judge.rednaga.io. But essentially, it uses all these features that we just talked about. We ran it across almost 200,000 samples. We had a subset of them already classified as malware. And then cross-validation thus far has shown that 97% can quickly say this is bad, this is not bad, or it's unknown. Honestly, unknown is the most interesting one to us because we say, okay, our model couldn't tell you if this was good or bad, but this might be worthwhile one person actually digging into and seeing what's going on. Maybe you can add a new feature from that. This service also has a JSON API in case you want to hook up to it. You might get rate limited because it's just a box in the cloud right now that's kind of slow. And it just has a simple interface. So he threw this up last week, and we already have about 3,000 submissions without telling anyone that this exists. So that's kind of interesting. You can see that it's basically saying that almost 2,000 of them are benign, about 1,000 of them are malicious, and then 41 are unknown. The 41 unknown are things that people in this room should dig into because these might be interesting binaries. So I know I skimmed over a lot of things. I know I went pretty fast. These are slides, or these are links to slides. I'm going to share this presentation, so don't worry if you can't write these down or anything. They're mainly on our GitHub. The training is for hunting O-days and how to reverse engineer things fast and how to think like a reverse engineer to say, I want to look for crypto. How do you look for crypto? The DEX education one is very deep into what does the DEX file look like and what is weird in a DEX file and how can we break tools. And then how can we patch those tools? And then there's some anti-emulator tricks. And then we also did some unpacking of basically every packer that was available on the market. It earned us 2 cease and desist letters and a potential jail sentence in China if we go. So apparently we did something kind of cool. There's a lot of white papers on DroidSec. They're good. There's a bunch of people in this room who wrote them, so you should bug them as well. And there's an Android cracking site. So, I know a lot of you guys were talking about secure development. Try and crack your own application. Try and do some cracking. If you can break it, someone else can. Anything can be broken. It's just a question of how long you want to spend on it and how much money you want to waste. And again, this is kind of like a Red Naga shout out. If you guys need help, ask. If you want binaries, ask. Literally, that's our big data. Send us one of those. We'll copy over 8 terabytes worth of APKs for you, and then we'll ship it back because it's actually faster than doing an SCP. If you want to send us your government implants, please do that. We've had 2 people send us implants that were on an agent's phone, apparently, and we wrote about them. We scrubbed all information that might have been bad, and then we burned them down to the ground. And it was great to see them squirm and see them pop up new C2s other places, and we can still track them. So make these people's lives hell. Help us out. We'll help you out. So thank you very much. Again, these are great people to follow. These are all interesting people, at least in reverse engineering or just in life. and they all have great advice, and they like to make fun of people, and it's hilarious. And half of them are in this room. So find them, make friends with them, and just make the community better. And thank you for having me, guys.
Okay, thank you, Tim, for your very interesting talk. Yeah, do we have any questions?
You get a beer if you ask me a question, or a non-alcoholic beverage, or a schnitzel.
Okay, I got a short, slightly off-topic question myself. It's like, how many of a time do you dedicate for Red Naga?
How much time?
Your personal time.
Too much. I mean, between the hot sauce making and reverse engineering, I don't know. Like, so Caleb and I live in the Bay Area. If any of you come out to the Bay Area, please send us a message. We hang out, we drink, we have a hacker once a month meetup, and honestly, we just brainstorm and we're like, why has no one done this? Okay, let's do it. Or we try and convince someone else at the hacker meetup to do it for us. So a lot of time.
All your time, I guess.
Yeah, pretty much. Yeah, we'll get that. It just got stood up like 2 days ago. I work at Cloudflare, so I'll figure out HTTPS someday.
I have a simple question about what you said before on the machine learning that you were using.
Yes.
Information I wanted to know roughly is which kind of information did you fed in to classify them?
So I wish Caleb was here to describe that. So Caleb wrote all the machine learning stuff. I don't honestly know, but I know it's written in Python, and it was using an off-the-shelf library of machine learning for Python. But it was just basically fed all the features that we just described. But I can't tell you exactly which one it was. I'm sorry.
Thanks.
Have you thought about automatically learning the features that you will then use for fingerprinting?
Yeah, I mean, I think that would be the next evolution of it. But so it's interesting and it's a great concept. But we basically knew all these features that we wanted to look for, and we had no idea if any of them would be interesting yet. So we started here, and we would love to take that next step and keep going. Honestly, this worked very well. So we could do that, or it's open source, and you can do that. We're not machine learning gurus. This was honestly kind of just we know how to reverse engineer things. How do I make this module? Okay, cool. Now we want to learn machine learning. Let's go to the next one.
Hello. When you've said that you managed to crack the packers,
Yes.
you were talking about the packers who are modifying the APKs or zips or whatever on the native level.
Yes.
Am I correct? So you managed to, for example, to crack the, I don't know, Tencent, Baidu, or Banco, or whatever.
Yes.
Those kind of things.
Yes. So we have a project online. It's I think it's on my personal GitHub, and it's just called Android Unpacker. It's a little out of date, but the stance I've always had is if you can point me to a file that you know is malicious and it's packed, and I have not released a unpacker for it, I'll release an unpacker. But all those companies are very lazy, in my opinion. Hopefully none of you are here. And if I release an unpacker, then they will immediately change it, and then I have to look into it again if I want to unpack that. So essentially, my goal or my suggestion to anyone trying to do this is have an unpacker and never release it until you want to make them change their algorithms, because they're just very lazy and they just don't bother. But yeah, all the Chinese ones are essentially based off the same code base and the same techniques. So if you set up a good kernel module to dump the memory, we have one that injects into the binary and waits for certain things. They're all pretty much publicly available, and it's like unpacking Windows binaries in the 90s kind of thing. Any other questions?
Yep. Here, was there any legitimate use of Smalley?
Yeah, so like Amazon used to use Smalley to inject DRM into every application when they first actually released the market. And it would be interesting because we would be using some techniques to make it so you can't use Smalley and it would break. And then their support would contact you and say, something's wrong with your binary, we can't put DRM in it. And we would say, well, we didn't check the box, so go away. So I guess that was a legitimate use. Other things are, we see lots of protectors that use it. Some of the packers will inject services into the binary so that they go first, so that then they can decrypt the rest of the binary. So I guess those are considered legitimate, but just annoying. Any other questions?
Okay, then thanks again, Tim.
Cool. Thank you.